All right. Hello, everybody, and welcome to the Morrison Planetarium, located here in San Francisco, California, on the unceded homeland of the Ramaytush Ohlone, who are the original inhabitants of the San Francisco Peninsula. My name is Katie. I'm in the booth behind you. I use she, her pronouns, and I will be taking you on our tour of the universe today. Throughout most of human history, we've only had our eyes with which to study and explore our universe. But these days, we have everything from telescopes, both on the ground and in space, to spacecraft that we send to explore other worlds, to use to learn about the universe around us. And we are going to be taking advantage of the data that all of these tools have collected as we travel through the universe seemingly faster than the speed of light using a free open source software called OpenSpace. If you have any questions about that software, you can come talk to me about it after the show. And so we are going to use that today to travel through the universe to learn what's out there and where we are in it. Before we get started, though, I have some housekeeping announcements. First, please turn off or silence all electronic devices, especially those cell phones. Keep them tucked away for the duration of the show. It's going to get pretty dark in here, and any excess light is going to be a distraction to those around you, and also ruin all the hard work your eyes have done adjusting to the darkness. There's also no filming or photography during the show. There is no eating or drinking in the planetarium, and for your safety, we ask that you remain seated for the duration of the show, as these stairs can be difficult to climb in the dark. We also don't want you blocking one of our projectors and creating a U-shaped hole in the universe. If for some reason you do need to leave during the show, please exit to the top of the stairs. Go up, not down. If at any time you feel any motion sensitivity, we recommend that you sit back, close your eyes, remind yourself that you're sitting in a stationary theater and not flying through space, and the feeling should pass. All right, last call for cell phones. Please make sure they're all tucked away, as any light is going to be projected up onto the screen and ruin the view for those around you. And please know that I can see all your screens from where I am up here. All right, and so with that, it's now time to sit back, relax, and enjoy our tour of the universe. All right, so we are going to start our tour off from a very familiar place, our home, planet Earth. Isn't it lovely? This is where almost all of human history has occurred, and where all human beings live. Well, almost all human beings. At any given time, scientists from countries all around the world are aboard the International Space Station, living and working together. And so this yellow trail that you see is the path that the space station is traveling as it goes around the Earth. And let's fly in a little closer to see what it looks like up close. Here we go. This space station is about the size of an American football field or 3 blue whales. So you may have seen our blue whale skeleton over by the rainforest. That will give you some sense of the size. 3 of those. The space station orbits only 225 miles above the Earth, circling our planet once every 90 minutes. This means that it's traveling at over 17,000 miles per hour. Now here's the part where I make a bad joke. I wouldn't want to have to pay that speeding ticket. Thank you. This is the furthest humans currently travel into space, but it's not the furthest that we've ever been. Between 1969 and 1972, human beings went to the moon. 12 NASA astronauts even got to walk on its surface. So let's fly a little closer so we can get a better look. And one thing I'm going to do right here is I'm going to turn the nighttime off. So at any given time, half the moon is in daylight, is lit up, and the other half is dark, just like it is with the Earth. I'm going to turn the night off, though, so that we can see the whole thing better. So the side we're looking at right now is the side you're probably most familiar with. It's the near side of the moon. The moon is tidally locked to the Earth, meaning that the period of its rotation, or 1 moon day, is equal to the period of its orbit, 1 month, or moonth, if you like. So because of this, we only ever get to see this one side from Earth. It's characterized by these big dark patches called maria, or the singular is mare, meaning sea in Latin. What astronomers once thought were bodies of water, we now know to be basalt plains. They are the results of ancient lava flow across the moon's surface. It wasn't until 1959, when the Soviet Union sent Luna 3 to the moon, that humans got a look at the far side of the moon, the side facing away from Earth, which is sometimes called the dark side of the moon. That's just because we can't see it. And what you might notice as we come around to that side of the moon is that it looks a lot different than the near side of the moon. It doesn't have so many of those big gray, darker gray patches, and it has a lot more craters. So that tells us that there wasn't any of that lava flow to fill them in. Also, there isn't any weather on the moon because the moon doesn't have much of an atmosphere. So there's nothing to cause erosion to fill the craters or change the moon's surface on this side. So because of that, we can learn a lot about the moon's history and the history of the solar system in general by studying these craters. The moon is 240,000 miles away from Earth, and it took the Apollo astronauts over 3 days to get there, traveling at 25,000 miles per hour. We're starting to get to speeds and distances that are hard to imagine, so let's switch to a more useful unit of measurement. One of the ways astronomers describe distances is in light years, light minutes, and light seconds. This tells us how far light, the fastest thing in the universe, travels in that given unit of time. The moon is about 1.3 light seconds from Earth, meaning that it takes light that was reflected off of the moon about 1.3 seconds to reach the Earth. It also means that when you're looking up at the moon, you're seeing it as it was 1.3 seconds ago. That's an important thing to remember as we get further and further away from home. The farther away something is, the further into the past we are seeing it. Now, the moon may be the farthest that humans have been, but we've sent spacecraft like rovers, probes, and landers even further. Now we're moving beyond the realm of Earth and out into the solar system. At the center of our solar system is our star, the Sun, which is about 8 light minutes away from Earth, or 93 million miles. Our Sun is a middle-aged star at about 4.5 billion years old. Orbiting around the Sun, among other things, we have the 8 major planets whose paths we can see here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now you might be asking yourself, what about Pluto? Why didn't you mention Pluto? It's my favorite planet. Well, Pluto was reclassified as a dwarf planet some years back, and for good reason, I think. So let's look at some of the things that make Pluto a little bit different. I'm going to put up its orbital path in a lighter blue color. And as we look at the solar system edge on here, one thing you might notice is that Pluto's orbit doesn't lie in the same plane as the orbits of the major planets. Its orbit is tilted with respect to them. So you can see it here. And if we look from above the solar system to get sort of a top-down view, you'll see that its orbit is also a different shape than the orbits of the major planets. The major planets, like Earth, orbit in almost a perfect circle around the sun, not quite a perfect circle. But Pluto's orbit is much more elliptical, or kind of egg-shaped, or more of an oval. It turns out it fits in a lot better with these objects. So this mess of lines you see here represents the paths of objects in the Kuiper belt, small icy bodies like comets and dwarf planets, orbiting the sun out beyond Neptune's orbit. In recent years, we've discovered some dwarf planets, like Eris, that are even bigger than Pluto. So I think if Pluto could feel, it would be happy with its new classification. Instead of being the smallest planet in the solar system, it's everybody's favorite, or at least the most well-known, dwarf planet. Pluto's orbit is about 10 light hours across, but it took the New Horizons spacecraft 9 years to travel there from Earth. So speaking of New Horizons, let's see how far human-made objects have traveled. New Horizons was launched in 2006, reached Pluto in 2015, and has been traveling through the outer reaches of the solar system ever since. In the 1970s, we launched Pioneers 10 and 11 and Voyagers 1 and 2 to visit the gas giant planets and collect data about them and take pictures of them. All of these spacecraft are traveling fast enough to escape the sun's gravity and leave the solar system behind. And even though they've been traveling for about 50 years, Voyager 1, which has traveled the farthest, still hasn't traveled as far as light makes it in 1 day. So now we're leaving our solar system behind and heading out into interstellar space, the space between the stars. The nearest star, Proxima Centauri, is 4 light years away. So compare that to the not even 1 light day that Voyager 1 has traveled. So now I'm going to turn on something called the radiosphere. Now, this is not an actual object that you would see if you were to travel this far out into space. It represents the furthest distance that human influence can be felt. In the 1930s, humans started emitting strong electromagnetic radiation in the form of radio waves, TV and radar signals, and atomic weapons detonations. These signals were strong enough to leave Earth. They travel at the speed of light, which means that the earliest signals have traveled about 90 light years. So that's the radius of our radiosphere here, is 90 light years. So maybe someone out there has detected our signals, but where could that someone be? Each of these markers indicates a star where astronomers have discovered 1 or more exoplanets. An exoplanet is a planet orbiting a star other than the sun. The ones within the radiosphere are the only ones that have had a chance of detecting our radio signals. The rest are too far away. But there are so many more out beyond that radiosphere. Astronomers now believe that most stars have planets orbiting around them, making our solar system the rule rather than the exception we once thought it was. One of the big topics of research these days is finding Earth-like planets with suitable conditions for life. We wouldn't be able to travel to these planets since it would take thousands of years to get there, but it's nice to know that they're out there. Now let's go beyond our stellar neighborhood and see what lies outside of it. Our little solar system lives in one of the spiral arms of the Milky Way galaxy. This is a computer model of what we think our galaxy looks like from the outside. We haven't actually traveled this far out into space, so we can't take an actual picture, but we can use our observations from here on the ground, as well as our knowledge of other galaxies to make a pretty good map. At the center of our galaxy is a supermassive black hole called Sagittarius A star. A black hole is a point in space that is so massive and so dense that not even light can escape from it if it gets too close. Most black holes are the remains of huge stars that have exploded. Supermassive black holes are much, much bigger and reside at the centers of galaxies. Sagittarius A star is about 4 million times more massive than the Sun, and all that mass is contained within a space with a radius only 30 times the radius of the Sun. A galaxy is more than just its black hole, though. The Milky Way contains more than 300 billion stars, which means there are likely billions of planets out there. It's 130,000 light years across. The amount of time it takes for light to travel from one end to the other is the length of the history of the human species. But that's just our own galaxy. 2 million light years away is the Andromeda Galaxy, our nearest major galactic neighbor. We have some dwarf galaxies that are closer to us, but Andromeda is the big galaxy that's closest to us. The Milky Way and Andromeda are hurtling towards each other and will collide in about 5 billion years, creating a new combined galaxy nicknamed Milkdromeda. And that is what they're calling it. I didn't make that name up for laughs. Now, you don't have to worry about this collision, though. Galaxies are mostly empty space, so there isn't much risk of our solar system colliding with another star. Also, life on Earth will likely have already ceased to exist by then because of the Sun's increasing size and temperature in its old age. The Milky Way and Andromeda Galaxy are only two of the many hundreds of billions of galaxies that comprise our known universe. As we zoom out, all the dots you're seeing represent not stars, but galaxies, each containing hundreds of billions of stars. Galaxies aren't evenly spaced. They tend to cluster together in groups. Andromeda and the Milky Way are part of what we call the local group, which in turn is part of a bigger cluster called the Virgo supercluster. So right now, what we're looking at is just data points telling us the locations of where we find galaxies. But we do have actual pictures of galaxies and galaxy clusters, like this one. This is the first deep field image taken by JWST. It shows us a galaxy cluster that's 4.6 billion light years away from Earth. This image contains thousands of galaxies, 84 of which are some of the youngest galaxies we've observed, aging all the way back to about 200 to 400 million years after the Big Bang. Not everything in this image is part of the cluster, though. These bright objects, you can see that kind of have points coming out from them, lines coming out from them. These are stars in our own galaxy that are in the same line of sight as this galaxy cluster. We also can see objects that are behind the cluster, like this space bacon up in the top rightish part of this image. So this galaxy appears stretched out due to an effect called gravitational lensing. According to Einstein's theory of general relativity, matter causes space itself to curve. The light from galaxies behind the cluster gets magnified and distorted because of this curvature. And so studying these effects of gravitational lensing can teach us a lot about galaxy clusters. In particular, they help us study dark matter, that mysterious, invisible matter that makes up about 25% of the universe. And there are a lot more interesting things we could talk about looking at this image, but we still have some more universe to see. So let's keep going. So looking back at our galaxy map here, you might notice it's kind of a funny shape. Looks a little bit like an hourglass or a butterfly. It makes it look like we are at the center of the universe, right? Here was Earth back at the center of our bow tie. We are not at the center of the universe. In fact, there is no center of the universe. It just looks that way from our data because of the limits of our observations. We can only see so far in every direction, so we create a sphere of data around ourselves. We are at the center of our observable universe. And the reason we have these big dark patches isn't because there isn't anything there. It's just that we haven't mapped those regions yet. The gas and dust of the disk of the Milky Way is blocking our view in those directions. Hopefully someday soon we'll have the tools to peer through that dust and make a more complete map. What we see will probably look the same as what we see in every other direction. Now moving out further, we're going to start to see some red dots at the edges of our hourglass. These represent quasars, or active galactic nuclei. These are the cores of young galaxies where gas is falling into the central black hole and extremely energetic electromagnetic radiation is being released. These are all billions of light years away, meaning that they existed in the earliest stages of the universe when galaxies were just beginning to form. If we could see what they look like right now, they might look a lot like our own galaxy, but we'll have to wait a few billion years to know for sure. And now let's zoom out as far as we can go. What we're looking at now is called the cosmic microwave background. It's basically the universe's baby picture. Isn't it cute? This light was emitted about 380,000 years after the Big Bang, which happened about 13.8 billion years ago. This is an image we get using radio telescopes. It shows us light that we can't see with our eyes. Another way to think of it is as a temperature map. On average, this radiation currently has a temperature of about minus 455 degrees Fahrenheit, or minus 270 degrees Celsius. But there are little tiny fluctuations, regions of slightly hotter temperatures and regions of slightly lower temperatures. Cosmologists study these fluctuations to learn about how the earliest structures of the universe formed, because a change in temperature will also tell us about a change in the density of the matter. This radiation comes from all directions all the time, but don't worry, it's not dangerous. It's very low energy. If you've ever seen static on an old television set, some of that static is coming from the cosmic microwave background. This is as far as we go. There's no light to see past this point. If we want to observe anything older than this, we'll have to come up with some other way to do it. So for now, let's head back home. People often ask me, as a planetarium presenter, what my favorite planet is, and I give them what seems like a boring answer: Earth. Earth is magnificent, and humans are perfectly suited for it. It provides air that we can breathe, water that we can drink. It has a magnetic field that protects us from harmful radiation from the sun. It provides trees whose shade we can sit under, flowers for us to smell, cats to pet, and dogs to play with. In the scheme of things, it may seem like a small, meaningless speck of dust, but to us, it's our only home. So when you next look up at the night sky, I hope you remember just how special our home truly is. All right, here we are again, home sweet home. There's no place like home.